Physics in 24 questions, 24 problems. So the goal here is to work through 24 problems in this textbook, Halliday Resnick, and use that as a means to talk about the physics. So I'm not going to cover everything. I'm going to cover the things I like. So we're in chapter 6, which is the same as chapter 5, but more. So last time I didn't do the problem first. Let's do the problem. The problem is a really great one. A car is driving around a banked curve. And in this case, the radius of the curve is 200 meters, and the angle of the bank is 10 degrees with the coefficient of friction of static friction of 0.6. So how fast can the car go without sliding off? It's a really great question. And it's got a lot of physics in there. In this particular chapter, Forces and Motion 2, really the big thing in here is friction. So they talk about friction, they talk about air drag, and then they talk about circular motion, which I kind of talked about before. And this has, most of those does not have air drag in there. Okay, so let's talk about friction. When you have two surfaces that are in contact with each other, then there's more than one type of force that we can have. They can push each other apart or prevent them from sliding through each other. So there can be what we call a normal force, and that's perpendicular to the two surfaces. And then we have another force that's parallel to the two surfaces that we call friction. And it's really an interaction between the atoms in the two materials that are, because they're not completely smooth, or even if they are smooth, they get close enough that they interact. It's actually quite complicated. However, we can model it in a simple way. And we actually have two models for friction. So the first model for friction is for when we have the two surfaces relatively stationary to each other, so they're not sliding, and we call that static friction. So for static friction, let's look at a case for static friction. And I want to show you something important about static friction with a simple example. So suppose I have a block on a table, and I know there's a gravitational force pulling down. I know there's a normal force pushing up, and those two are equal because it doesn't accelerate up or down. And then I push this with my finger with a force of 1 Newton x hat. And it doesn't move. It doesn't slide. It doesn't accelerate. Well, then I know that the net force in the x direction, F net in the x direction, is 0. I know that has to be true, right? Because it doesn't accelerate. So that means that there's a backwards pushing frictional force, F friction. And in this case, that would be equal to 1 Newton. Now, what if I increase my pushing force to 2 Newtons? And it still doesn't move. Well, then that has to be 2 Newtons. Right? It has to be. So if I push harder, that pushes harder. If I push, now go back to 1 Newton, and that stayed at 2, then we'd have a net force pushing this way. I'd push the block, and it would accelerate that way. Weird. Doesn't happen. Okay? So this force, this frictional force, is a type of force of constraint. It says, I'm going to do whatever I need to do in order to make that thing not move. Of course, there's a point where it doesn't work anymore, and that's what we call that's where we get the maximum coefficient of friction. So we get the following model for this magnitude of the frictional force. Capital Fs for static, less than or equal to a coefficient, that's the Greek letter mu, times the normal force. That's really important. So but this less than or equal to says that it can be whatever it wants. It could be 0, right? If I don't push on this and I calculate mu times the normal force, then there's going to be a force pushing it back and it would accelerate, and that doesn't happen. Okay, so that less than or equal to is very important. A lot of times we'll deal with the maximum frictional force or the minimum coefficient of friction. But that's what we call the coefficient of friction of static friction. I don't know if I can write it out loud. Why am I writing that at all? Okay, and this coefficient depends on the two types of surfaces interacting. So maybe it's wood on chalkboard, and that has a particular static coefficient of friction, or it could be chalk on chalkboard. I don't know. It could be any two materials. They have a different coefficient of friction for how they push together. Also notice that there's no negative signs here. It's a force that pushes to prevent the sliding. Okay, so it doesn't always have to be in the opposite direction of the push. It depends on the situation. So just be careful of that. It has to be parallel to the surface and in the opposite direction to prevent it from sliding up to that maximum point. So again, this is not a vector equation because that's a vector force, that's a vector force, but they're in different directions. So you can't really say they're even equal to each other. Okay, but that's our model for static friction. Now, when the two surfaces are actually sliding, then we have a different model, and it looks like this. F kinetic is equal to the coefficient of kinetic friction times the normal force. Now, it's just a value. And it's, again, in the direction parallel to the surface to prevent things from moving. So it wants to make them stop sliding. Okay, so those are our two models for friction. I want to point out that this is a model. Like all models in science, they're only kind of right. They're never perfectly right because we don't know everything about everything. And even in this case, these models right here, we can find cases where it doesn't really work, right? If you push things together really hard, the friction force stops increasing at some point. So there's a bunch of weird stuff like that. But that's friction. And we're going to do a friction problem right there. I do want to talk about the other things in the chapter. And now I want to remind you very importantly of where we're at. We're at this. F net is mass times acceleration, right? So force is a vector, acceleration is a vector. This is Newton's second law. This says that the relationship between the net force and the acceleration depends on the mass of the object. And we talked about acceleration as this, the change in velocity with respect to time. You could also write that as a derivative. That's fine. It's the derivative of velocity with respect to time. But that's a vector. That's the vector. So it's possible to change the direction of the velocity vector and not change the magnitude and still have a change in velocity, right? Because the velocity depends on the direction. You know, imagine this. I'm going 1 meter per second that way, and then I'm going 1 meter per second that way. I didn't change my speed, but I definitely had to accelerate. Okay. And if we have an object moving in a circle with some velocity v, and the radius of the circle is, I'll use r, then the velocity does indeed change, and the direction of that change in velocity is towards the center of the circle. So that's a hat, that's the direction of the acceleration, and the magnitude of the acceleration is v squared over r. Now, it is possible that it could both be changing direction and speeding up. And so that's a little bit more complicated case. We're going to deal with situations that are just either speeding up, slowing down, or changing direction. If they're doing all of those things at the same time, then you could just use delta v over delta t if you know those two changes in velocity. Okay, let's look at the last thing in here. And I want to point it out because here is where I would do Python. I'm not going to do Python today, but I want to point it out. So suppose you take a ball, two balls, and you drop them from the same height. And they have the same size, but this has a mass of 0.01 kilograms, and this has a mass of 10 kilograms. Well, the gravitational force on this one's going to be way greater than that one. But if that's the only force, that gravitational force, since it depends on mass, means acceleration is going to be independent of the mass because that mass cancels. But we have a good feeling about dropping objects of different masses that they don't exactly follow the same rate. And that's because as these things move through the air, there's also a backwards pushing air resistance force or drag force. And this drag force we can write as, I think they call it drag. There's more than one model for this because it's complicated, but here's the most common one, 1/2 rho, I'm going to re-erase that, 1/2 rho a c v squared. So this is the number 1/2. That's the density of the air. That's the cross-sectional area of the object, right? So in this case, if I drop a ball, that'd be the area of a circle. That's a drag coefficient that depends on the shape of the object, and that's the velocity. But here's the kicker, okay? Let's just suppose I drop an object vertically, and it's a ball, and I can say F net in the y direction is going to be the upward force. This is going to be an upwards force because the velocity is moving down. If you put in a minus sign here, it's just for fun, unless you make this a vector. And there is a way to do that, but the book doesn't do that. So in this case, I know the drag force is up, 1/2 rho a c v squared minus mg equals may. All right, so that's my net force, mass times acceleration in the y direction. And I could solve for this acceleration, and that tells me how the velocity changes, right? Acceleration tells me how velocity changes. Imagine that I wanted to integrate and find the velocity as a function of time. Well, that is not easy, because if I take this as equal to m dv dt, and what we did before was we multiply both sides by dt, that's cool, but I got a v on that side. So there's a couple tricks. In this case, it's actually a very difficult problem because I can't even get all the v's on one side. If there's no gravity, it's not too terribly difficult, but it's not a simple problem. It's not. And in fact, once you start moving in 2 dimensions, this force depends on both the x and the y force. So it's really, 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 really tough. Now, one super great way to solve this problem is to break it into small time steps. So this is the object at different time intervals. And during each one of these short time intervals, I can assume that this is constant, even though it's changing, and use that to find the acceleration, and then use that to update the velocity and the position. And that's what we do in a numerical calculation with Python, but I'm not going to do that. Not now, because I'm doing this problem, right? OK, so there we go. We're ready to do the problem. I mean, this is kind of fun, right? It's kind of like physics haiku, because you're like limited to 3 lines and 5 syllables or something like that. So I'm limited to this problem to explain physics. So it's going to kind of help me be not so long. Because I could talk an hour about this chapter. I'm not going to. Let's just do the problem. So I have this car coming out of the board this way. And I want to find out how fast it can go. I want to find the velocity. Well, the first thing I'm going to do is to draw a free body diagram. So let's just draw the car again right here. And there's my car. And it doesn't have the headlights, it doesn't have the grille, it doesn't have the tires, because I just want to make it a little bit easier. What forces are acting on the car? Well, the first thing we want to do is what long-range forces act on the car. There's only one that you'll see right now, and that's the gravitational force. So the gravitational force pulls straight down. I'm going to write that as mg. Now I need to think about contact forces. What's in contact with the car? It's really just that banked road. So the banked road is pushing on the car, and we can break that into a normal force and a frictional force. So a normal force would be perpendicular to the surface. So I'm going to draw this right here. Like that. Perpendicular, not up, not the opposite direction of g. And now the friction force wants to prevent the object from sliding. So imagine that I'm going too fast, right? Well, the car would, kind of want to move in a straight line, which is up the bank, right? So if this is going in a straight line, and since this road curves, that means it wants to go that way. So that means that the frictional force, I'm just going to call it FF, would be that way. When we draw a free body diagram, we always want to pick our x and y coordinate next. And here's a trick. You want either the x or the y axis in the direction of the acceleration if you can fix it that way. Because then you're going to have one of the components of Newton's second law be equal to 0 and one just a mass times acceleration. So in this case, the car is accelerating, right? It's moving in a circle. And the direction of the center of the circle is that way. So the acceleration is going to be towards the center of the circle that way. So I'm going to pick this as my x-axis, and that is my y-axis. Now I need to do one other thing. I need some angles. So this is the angle theta right there. So that's also the angle theta. And this is the angle theta. Right? So you can do a little geometry to see that. Is that the angle theta? Yeah, OK, good. Now I can go ahead and write down Newton's second law. I'm going to write it as 2 scalar equations. So my first scalar equation is going to say this, F net in the x direction is going to be what forces act in the x direction. Okay, so let's just look. Does gravity act in the x direction? No. Does friction? Well, yeah, it does, right? There's a component of the frictional force. Let me just draw that one frictional force like this. There's my frictional force. This is my x component of the frictional force. That's my y component of the frictional force. And that's the angle theta. It looks like a 0 theta. So if this is F friction, this would be F friction cosine theta, right? Because it's the adjacent side of that triangle. So the x component of that is going to be F friction cosine theta. Are there any other forces in the x direction? And yes, there are, right here. I have the normal force has a component in the x direction. Okay, now I kind of need to find out what that angle is. Let's see, this is the angle theta, right? Because these are parallel lines. And you can play with some geometry there, but yeah, that's good. So here, this is going to be my x component, and that's my right triangle. So that's the opposite side of the right triangle. So this is going to be in sine theta. And it's also in the positive x direction. Plus in sine theta. Please tell me I'm not running out of room. I'm not. OK. And that's going to be equal to mass times acceleration. But in this case, acceleration is acceleration due to moving in a circle. So this is going to be equal to mv squared over r. Almost ran out of room. Didn't. OK, so that's a good equation, right? I don't know the frictional force. I know theta. I don't know the normal force. I know theta. I don't know the mass. They didn't give it. I don't think we're going to need it. And I'm trying to solve for v, and I know r. Okay. Now let's do the same thing for the y direction. F net in the y direction. Okay, what forces are in the y direction? Well, I have, again, the normal force. I have this side of the normal force is going to be the y component. So that's the adjacent side of that triangle, so it's going to be cosine. In cosine theta. And then I have part of the friction force. You think friction doesn't act in the y direction. It does here. Okay, so part of the friction force is in the y direction. That's going to be minus FF sine theta. And then I have the gravitational force minus mg. And that's equal to 0. So let's go again. How many of these things do I not know? I don't know N. I don't know the frictional force. That's it. I only know 2 things I don't know right up here. But then up here, I also don't know V. So there's actually 3 things I don't know in these 2 equations. That should be a big hint right there, right? If there's 3 things I don't know and I have 2 equations, what do? I need another equation. And so that other equation is my model for friction. F friction is equal to the coefficient of static friction times the normal force. Now, here it's equal to because we're at the maximum velocity. We're going to find the maximum velocity, so we're doing the maximum friction. So now I have 3 equations, 3 unknowns. Let's start getting to it and solve this dumb thing. It's not dumb, it's actually a good problem. Okay, I'm going to go ahead and substitute in the friction force into both of these equations because I obviously don't care what that is. So every time I see friction, I'm going to write mu s times n. So I'm going to put mu s times n right there and mu s times n right there. And let's just write this first equation up here. So I get mu. I'm just going to write it as mu. Is that okay? Just to make things simpler. I'm going to write it as mu so that we don't have to write so many subscripts. Because there's only one kind of friction. Mu n cosine theta plus n sine theta equals mv squared over r. And then this equation is going to be n cosine theta minus mu n sine theta. I'm going to say equals mg. Right? I just added the mg to the other side. Okay, I did that, so now I can get rid of this stuff over here. Because now I have 2 equations, 2 unknowns. Right, I don't know n and I don't know v. That's it. So I just need to solve for these 2 equations. Now, I mean, we can do a little trick. I mean, tricks are kind of fun. No, we can't. I was going to add these 2 equations, but let's not do that. I'm going to solve this one for n cosine theta. If I do that, I'm going to get no. I just need to solve for n. I think I'm going to make a mess. And that's what makes this a hard problem. Getting here is physics. The rest is just algebra. And I know that sounds terrible to say it, but it's just totally true. So I'm going to solve this one for n. I'm not sure why I picked that one. So I'm going to factor out the n times cosine theta minus mu sine theta equals mg. And then so n is equal to mg over cosine theta minus mu sine theta. Now I can substitute that in up here. I'm going to actually factor out the n first. So I get n times mu cosine theta plus sine theta equals m v squared over r. And then I can substitute in for this n. And I don't need to solve for that. I want to keep that v on the other side because that's fine. So all I'll do is substitute this in. I get mg times all that, mu cosine theta plus sine theta, and then I have to divide by this, cosine theta minus mu sine theta. And that's going to be equal to m v squared over r. Oh, look. The mass does indeed cancel. That's a big thumbs up right there. No, it doesn't want to do it. Thumbs up. There it goes. OK. And then multiply by r, and I get v squared. OK. So let's just say v squared is equal to gr mu times cosine theta plus sine theta over cosine theta minus mu sine theta. OK. I'm going to go ahead and plug in my numbers. Before I do that, I want to check the validity of my solution. Because I get something like this, it could be whack and wrong. So how do you know it's wrong or not wrong? Well, let's check the units, right? So G has units of newtons per kilogram or meters per second squared. So if I get meters per second squared times meters, I get meters squared per second squared, and that should be the units for velocity. So mu has no units, cosine has no units, none of those have units. So I get the right units. That's good. Okay, now what about this? As the coefficient of friction increases, I should be able to go faster. Right? So if I increase the value of mu, what happens? It's not completely clear here. So that's not trivial. One thing I could do, and I'm going to let you check this. I'm pretty sure my answer is right. What if mu goes to 0? Well, in that case, there is a maximum. You can have a banked turn for no friction. And that's what you could solve for. So you could check that and see if you get the right solution. And the other thing you could check is what happens when theta goes to 0. When theta goes to 0, you have a car on a flat plane, and that's another solution. So these are two different problems in the chapter that you can check if this gives you the same solution. Let's go ahead and plug in our numbers. So I'm going to put in, like I said, just because I know you guys want the numbers. So G is 9.8, R is 200, mu is 0.6, and theta is 10. So I'm going to put all this in my calculator and see if I can not make a mistake. I'm going to use this Hewlett-Packard calculator. And I'm taking off my glasses this time so I can see better, because a lot of times I can't see the calculator. OK, 9.8, enter 200 times. And then I'm going to do this, 0.6, enter 10. Am I in degrees? Let's do 10 cosine. Yeah, I think I am. Times, and then 10 sine plus, and then times. And then I'm going to do 10 cosine, and then I'm going to do 0.6 enter 10 sine times minus divided by. No way. Oh, that's... I got 1701. I'm like, there's no way. But that's v squared. So now I'm going to take the square root, and I get 41. Where's my chalk? So V max is 41 meters per second. There you go. OK, there's a bunch of other good problems in there, but you know, the playlist says 24 problems, so I can't do any more unless I change the rules later. But the playlist for all the rest of the videos are down below. Hope you enjoy that, and we'll do the next chapter next.